So, JWST just dropped the most detailed map ever made of the cosmic web, the giant invisible structure that holds the universe together. And the picture they got back is doing two contradictory things at once. The cosmic web used to be a galaxy accelerator. Then, somewhere in the last few billion years, it became a galaxy killer. Same structure, opposite outcome. That is the part that needs explaining. The new map covers almost 14 billion years of cosmic history in one continuous slice. The study is called Large-Scale Structure in Cosmos Web. It was just published in the Astrophysical Journal, led by Hossein Hatamnia, and a long list of co-authors. And here's the part that should grab you. They reconstructed the skeleton of the universe in 3D using 164,000 galaxies as anchor points, going back to when the universe was only about 1 billion years old. Now, before we get into why that flip happened, let's talk about what the cosmic web actually is. The cosmic web is the largest scale structure in the universe. Galaxies aren't scattered randomly through space like sand. They're collected along enormous strands of dark matter and gas, called filaments, that stretch for hundreds of millions of light years. Where filaments cross, you get clusters, basically galactic cities packed with thousands of galaxies. Between the filaments, you get voids, enormous, mostly empty regions of space. Picture a soap bubble foam. The walls of the bubbles are filaments. The intersections where bubbles meet are clusters, and the empty insides are voids. Galaxies live on the bubble walls, not in the empty middles. This structure isn't just an aesthetic. It's the framework that decides where galaxies grow and how fast. Dense parts of the web pull in matter through gravity. That matter cools, forms stars, and assembles galaxies. So the web is the universe's growth blueprint. Map the web, and you map the conditions that produced every galaxy you can see. Here's the problem. Mapping the web is incredibly hard. You need galaxy positions in 3 dimensions, and the hard part is distance. You can't just look at a galaxy and tell how far away it is. You have to measure its redshift, which tells you how much its light has been stretched by cosmic expansion. Without redshifts, all your galaxies pile up into a flat 2D smear. This is where JWST changes the game. The team used the Cosmos Web Survey, the largest JWST program ever conducted. 255 hours of observing time, a continuous patch of sky about the size of 3 full moons. Deep imaging in 4 near-infrared filters with NIRCam. From that, they extracted photometric redshifts for 164,000 galaxies, then ran a weighted kernel density estimation across cosmic time slices to produce a 3D density map of the entire web. Okay, so now we get to the actual findings, and this is where it gets interesting. Finding number 1. More massive galaxies live in denser regions of the cosmic web. That's true across all cosmic time sampled, from the modern universe back to redshift 7. The biggest galaxies have always been packed into the densest parts of the web. Seeing that hold across nearly 14 billion years is the important part. Environment has shaped galaxy growth from extremely early times. Finding number 2. Between redshifts 2.5 and 5.5, when the universe was 1 to 3 billion years old, the mass density connection gets unusually strong in the densest regions. The team reads this as evidence for early protocluster assembly. Protoclusters are the ancestors of today's massive galaxy clusters, and they were already taking shape when the universe was a small fraction of its current age. This connects directly to the broader JWST mystery. Over the past few years, JWST has been finding galaxies that look too mature too early. Brighter than expected, more chemically developed than expected. The cosmic web map gives a possible answer. If some of those galaxies formed inside rare, overdense regions, they had access to more raw material faster than average. The web could be the environmental machinery that explains why the early universe looks so developed so quickly. Finding number 3 is where things flip. In the early universe, dense regions had more star formation. Galaxies in crowded parts of the web were forming stars faster than galaxies in emptier regions. The dense environment acted like a feeding ground. Gas got pulled in, accumulated, and fueled rapid star formation. Crowded was good, but starting around redshift 1.2 and continuing into the modern universe, that relationship reverses for quiescent galaxies. Dense environments suddenly correlate with less star formation. Galaxies in clusters and dense filaments stop forming stars, while their counterparts in less dense regions keep going. The same structure that used to feed galaxies starts choking them. This is called environmental quenching, and the effect gets stronger for smaller galaxies. Below about 10 billion solar masses and at redshifts under 0.8, the cosmic web becomes actively hostile to star formation in low-mass galaxies. Their gas gets stripped, heated, and they slowly fade out. So what changed? The leading explanation is that as clusters mature, their gravitational potential wells deepen, and the hot gas between cluster galaxies gets hot enough to actively damage smaller galaxies passing through it. Their fuel gets blown out by ram pressure stripping. Once the fuel is gone, star formation stops. In the early universe, clusters weren't big enough yet to do that, and the gas was cooler and more plentiful. The web fed galaxies. Later, the same web starves them. In short, the cosmic web is both a maternity ward and a graveyard. It depends on when you visit. Now let me put some honest fences around the result. This isn't a map of the entire universe. Cosmos Web covers about 0.6 square degrees, which is huge by deep survey standards, but still a tiny window onto the full sky. The team's conclusions hold up because they have 164,000 galaxies inside that window, but they're sampling one cosmic neighborhood. This also isn't a direct image of dark matter. The web includes dark matter, gas, galaxies, and voids, but what the team mapped is the galaxy density distribution. Galaxies trace the dark matter scaffolding, so the map shows where dark matter is, but only indirectly, and the photometric redshifts have uncertainties. They're estimates based on filter colors, not precise spectroscopic distances. The reconstruction accounts for this with weighting, but the time slices are fuzzier than they would be with full spectra. So what does this all add up to? The cosmic web is the universe's growth blueprint, and JWST just gave us the most detailed look at how that blueprint operated across nearly the entire history of cosmic time. Galaxies aren't just objects, they're inhabitants of a structure that shapes them, and that structure has been flipping its role from accelerator to regulator as the universe aged. We are no longer just looking at individual weird galaxies in the early universe. We are starting to see the environmental machinery that built them. What do you think the next step is? Hunting for the most extreme early protocluster pockets? Or pinning down exactly when the web turned hostile? Let me know in the comments which direction excites you more, and if you want more breakdowns like this, watch the video that is on your screen.